What's up, Ninja Nerds? In this video, we're going to be talking about fatty acid synthesis. This is part 2. If you guys haven't already seen part 1, go click on that, go check that out, really understand that, because we're going to go and dive into the really deep depths of fatty acid synthesis. And again, this is part 2. Before we get started though, please, if you guys like this video and you guys really enjoy what we do, please continue to support us by hitting that like button, commenting down in the comment section, and most importantly, subscribe. All right, Ninja Nerds, let's get into it. All right, Ninja Nerds, so when we talked about in part 1 of fatty acid synthesis, we went over basically all of this stuff. Let's just quickly recap it. And then what I want us to do is at the end of part 1, our goal was to be able to develop a couple substrates, 3 in particular, that we need to start building our fatty acid chain. Let's quickly recap what we covered in part 1. We need to perform fatty acid synthesis. What do we really need? Okay, we start off with glucose, right? Glucose gets converted into pyruvate via the glycolytic pathway. Then pyruvate will get taken up into the mitochondria in the presence of oxygen. So in this situation here, you would need oxygen present in order for pyruvate to get converted into acetyl-CoA, to get taken up into the mitochondria. Once it's in the mitochondria, what happens with that acetyl-CoA? Well, you know, acetyl-CoA will combine with oxaloacetate and make citrate. And then citrate will have to go through the Krebs cycle, and eventually you'll make NADHs, you'll make FADH2s, that'll go to the electron transport chain, you'll make ATP. The problem is, when you're making fats, the issue is that you already have too much ATP. There's already too much ATP that's being produced within these cells. So if there's too much ATP, because maybe you are already having a lot of glycolysis that's occurring, you're having a lot of fatty acid oxidation that's occurring, a lot of oxidative deamination that's occurring. Either way, there's lots of ATP. We don't need to make any more. So whenever there's lots of ATP, there's a very particular enzyme, right, that is designed to be able to convert citrate into isocitrate. Okay, but that enzyme is inhibited, and so citrate isn't able to be converted into isocitrate and go through the Krebs cycle because of high ATP, and so that'll inhibit this continual cycling of the Krebs cycle. When that happens, citrate starts to build up. Okay, so you start getting lots and lots of citrate. As that citrate builds up, what happens is there's a very specific protein present on the mitochondria that can spit citrate out of the mitochondria and into the cytoplasm. Once that protein allows for citrate to go out of the mitochondria and into the cytoplasm, something very interesting happens. There's a very special enzyme called citrate lyase. And what citrate lyase does is it basically undoes the reaction of when we went from acetyl-CoA and OAA to citrate. We're just going backwards. So citrate lyase cuts citrate and gives you oxaloacetate and acetyl-CoA. But in order for us to be able to convert citrate into oxaloacetate in acetyl-CoA, this isn't citrate-CoA, so what do we have to do? Citrate lyase cuts citrate into OAA and acetyl group, so we have to add a CoA on. Now, let's go up this pathway for a second. What happens with that OAA? The OAA, the oxaloacetate, will get converted into malate. Now here's what I want you guys to remember, which is important. Malate will eventually get converted back into pyruvate. And basically all you're doing here is you're going from this is actually going to be what? A 4-carbon structure, and then you're going to a 2-carbon structure when you go from malate to pyruvate. There's an enzyme that catalyzes this step, and this is called a malic enzyme. What I want you to remember is that the malic enzyme is important for converting malate to pyruvate, but also within that step of going from malate to pyruvate, you generate some very important molecules that we're going to need as precursors to fatty acid synthesis. And this is NADPH. I want you to remember NADPH as one of the 3 things that we need to start building the fatty acid chain. I want you to remember that this is the guy with what's called the reducing power. It's going to be a very strong molecule that we use to reduce particular molecules in the fatty acid synthesis pathway. Okay, so that's one way that we get NADPH, is from converting malate to pyruvate via the malic enzyme. Another way that we get NADPH, you guys know another way? You know, there's a very specific pathway called the Pentose Phosphate pathway. The pentose phosphate pathway, a very, very brief discussion here, is we take glucose, right? And we convert it into what's called glucose 6-phosphate via the hexokinase enzyme or glucokinase enzyme, depending upon what tissue we're in. Then glucose 6-phosphate, you know what happens is it can eventually go down the glycolytic pathway, or it can go into what's called the pentose phosphate, where eventually it gets converted into what's called ribose 5-phosphate. And then during that process of where you make ribose 5-phosphate, you can generate NADPHs. So from the pentose phosphate pathway, we can generate lots of NADPHs, as well as we can generate NADPHs from the malic enzyme converting malate into pyruvate. Now we have that one precursor. We got two more that we have to talk about. The other precursors, we have to go down this pathway. So we take citrate. We had the citrate lyase cut it to give us OAA, to give us malate, to give us eventually pyruvate, to give us an NADPH. The other component is we go to AcetylCoA. Now what happens with the AcetylCoA? The AcetylCoA is a what? It's a 2-carbon structure. What I want to do is I want to add on another carbon to it. So I'm going to do what's called a carboxylation reaction, where I add a CO2 onto AcetylCoA to make malonyl-CoA, which is a 3-carbon structure. So this carboxylation reaction requires an enzyme, which is called AcetylCoA carboxylase. And we talked about this in great detail in the part 1. This is an important enzyme. The reason why is that this enzyme requires lots of things. It is basically the rate limiting step within fatty acid synthesis, highly regulated step. Lots of things can alter or modify the activity of this enzyme, which determines this type of reaction, going from AcetylCoA to malonyl-CoA. Why is this so important? Malonyl-CoA is one of the other substrates. This is going to be the building block, if you will. I like to remember this guy as the building block for fatty acid synthesis. I need him in order to keep building my fatty acid chain. So very, very important to remember malonyl-CoA. Really quick recap of the AcetylCoA carboxylase. This enzyme catalyzes this step, but there's enzymes and different types of molecules that either allosterically regulated or regulated by phosphorylation reactions. If you guys remember, insulin can help to stimulate this enzyme. Okay, so it has the ability to stimulate this enzyme by pulling phosphates off. Citrate can allosterically regulate the AcetylCoA carboxylase enzyme. It can bind onto a particular portion of it, change its structure, making it more active. Particular hormones like glucagon, norepinephrine, epinephrine, they have the ability to regulate protein kinases, which will phosphorylate the AcetylCoA carboxylase, inhibiting this enzyme. And then long-chain fatty acids. Think about this one. What's the goal of making these molecules? To make fatty acids. If you already have lots of long-chain fatty acids, would you want to make more? No. So it's kind of going to act as a regulator, being able to say, hey, too many fatty acids, don't stimulate this enzyme because I don't need any more of this because I don't want to make more fatty acids. So again, that's the process. And the other way I like to think about insulin and then glucagon as the opposer is insulin loves to build things up. So it wants to make fat, make protein, make glycogen. Glucagon, norepinephrine, epinephrine, these are stress situations. They want to break things down. They want to break down glycogen. They want to break down lipids, okay? So very important to remember that. All right, so we have the two things we have. NADPH, one from the pentose phosphate pathway and from the malic enzyme pathway. We have malonyl-CoA, which we got from AcetylCoA being carboxylated by this important enzyme called AcetylCoA carboxylase, which is a rate-limiting step in fatty acid synthesis. Highly regulated. What's the next thing that I want you to remember? Before we go into the third substrate, there's another thing that you need to remember about malonyl-CoA. It's really good, not only at being able to be a very important building block for fatty acid synthesis, but it also can regulate the activity of very particular types of proteins which are present on the mitochondria. You know, in the mitochondria, you have different types of proteins here that we have them kind of listed here in pink. It's kind of beautiful in that sense. Look, you see this? It's in the shape of a 1. This is actually called CPT1. Sometimes we also call it CAT1. Carnitine palmitoyl transferase type 1 or carnitine acyl transferase type 1. And this one is carnitine palmitoyl transferase type 2 or carnitine acyl transferase type 2. Either way, malonyl-CoA inhibits this enzyme, okay? The carnitine palmitoyl transferase type 1. In general, why is this important? You're probably like, what the heck does this have to do with anything? You know these proteins, they're important for basically allowing for the translocation of fatty acids into the mitochondria, because once these fatty acids get into the mitochondria, they go through a process called beta oxidation. And beta oxidation basically is going to be used to make ATP. Well, we already have too much ATP. So if we have so much ATP, do I want more fatty acids coming in here getting oxidized? No, I'm trying to build fats up. So when you have lots of malonyl-CoA, it inhibits these carnitine palmitoyl transferases so that no more fatty acids get taken up to get broken down so that we can build them. Isn't that cool? I think it's pretty cool. All right, the last substrate or kind of thing that we need here, we have NADPH, malonyl-CoA. The third one is a very particular enzyme. What is this enzyme? Let's take a look here. This enzyme here, in purple, is called the fatty acid synthase, type 1. What is this purple enzyme here called? This is called fatty acid synthase, type 1. We're going to call it FAS1. This is a very special enzyme. Now, this enzyme, FAS1, has two particular components on it that you actually do have to know, and we're going to go into most detail of it throughout the video. On one end of it, it has a cysteine residue with a thiol group. Okay? And on the other end, it has this ACP structure. What the heck is this? ACP is basically the acyl carrier protein. And what happens is there's a structure here called a 4-phosphopentathione that makes up this ACP kind of group with the sulfhydryl group. But all I want you to know is that there's two components of the fatty acid synthase. And this is the enzyme that we're going to be utilizing to make fatty acids. There's two components of it. One is the cysteine component with the sulfhydryl or the thiol group. And then the second one is the ACP group, which is the acyl carrier protein, which has the sulfhydryl group. These are the very, very important components here. So we have three components for fatty acid synthesis. NADPH, which is the reducing power, malonyl-CoA, which is our building block to make fatty acids, and then fatty acid synthase type 1 is our enzyme, or the catalyst, if you will, that's going to help to propagate this entire process. So now that we've built our building blocks, we have the things that we need, let's actually go through the process of how we build fatty acids. All right, engineers, so we have to go through step by step and build up this fatty acid chain. So we have our three precursors. We're going to use them sporadically throughout these different steps. Okay, so again, remember what were those three things? NADPH, malonyl-CoA, and then the last one is the fatty acid synthase type 1. There is another player that kind of like pops in every now and then, and it's AcetylCoA. And again, he's an additional one that will be floating around that we can have in there. So if you really want to, you can have 3 plus an additional one, AcetylCoA. So a malonyl-CoA, an AcetylCoA, an NADPH, and then the fatty acid synthase type 1. All right, let's go through step 1 here. Step 1 is we have to add an AcetylCoA group onto the ACP end. That's the first thing that has to be done. So we're going to add an acetyl group. An acetyl group is how many carbons? 2 carbons. I want you to remember that. So what I'm going to do is I'm just going to draw circles, which is going to represent my carbons here. And then again, this is AcetylCoA, so it's going to have that coenzyme A popping off here, right? So what I'm going to do is I'm going to add this into the first step, and I'm going to add it onto the ACP end. Right? The second thing is when I add this AcetylCoA group on, I can't have the CoA because I need that end to add it on to the ACP. So I'm going to pop that CoA off in this step. Now the enzyme that is utilized in this process here is a very special enzyme, and this enzyme is called acetyl transacylase. So again, all this enzyme is doing is it's transferring the acetyl group, the 2-carbon group of acetyl-CoA, onto the ACP end. So what would it look like over here then? If we were to have the result of this step, we would have, again, a 2-carbon kind of molecule hanging off of that ACP end. Particularly, if you really want to be particular, it's going to be binding to that sulfur group there on the actual thiol group, on the sulfhydryl group. Okay? So that's the first step here. The second thing that we're going to do, okay, so first thing, we added an acetyl-CoA group onto the ACP end, use an enzyme called acetyl transacylase. The second thing that we're going to do is we're going to have, let's pick up where we left off here, where we had the 2-carbon structure here, the acetyl group hanging off the ACP end. Now what I want to do is, I need room for the malonyl-CoA to bind onto that ACP end. So I can't have these 2-carbon groups sitting here. So what I'm going to do is I'm going to transfer these 2-carbon groups onto the cysteine residue. I'm going to transfer it from the ACP end onto the cysteine end. So an enzyme is utilized to transfer that. And we call this enzyme acyl, not acetyl, acyl acylase. Okay? And what is going to happen in this step is I'm just going to transfer these 2 carbons onto the cysteine group. So what would that look like over here? So now what I would do is I would have the 2 carbon groups hanging off of the cysteine group, the acetyl group there, and then if we were to just be particular here, the ACP group is now going to be back to that sulfhydryl component like that. Okay? So that's that step. And here we can just kind of put here, to make it easy, we can put a transfer of these 2 little acetyl groups there. Okay, that 2-carbon acetyl group. All right, that's the second step. So first one, add an acetyl group onto the ACP end. Second step, transfer it from the ACP end onto the cysteine end. It's kind of like, why didn't I just add it to the cysteine in the first place? Who knows why these things happen? All right, the next thing, the third step here. So let's pick up, we have the 2 carbons here on that cysteine end. Now I have space here on that sulfhydryl group, okay, to be able to add on my malonyl-CoA. So what can I now add? What I'm going to do now is I'm going to add on a 3-carbon structure, because you know malonyl-CoA is a 3-carbon structure. We've already discussed that. So we're going to add a 3-carbon structure in the form of malonyl-CoA, but we can't have the CoA because we need that end to bind to the actual ACP group, so we pop off that CoA. In order to do that, I need a very special enzyme to catalyze this step. And this enzyme is called malonyl transacylase. And all we're going to do is we're going to add the malonyl group onto the ACP end. So let's look at what this would look like afterwards. We still have that 2-carbon acetyl group on the cysteine residue, bound particularly to the thiol group. And then the ACP component here is going to have that malonyl, that 3-carbon structure, which is going to be bound to it. Okay? Beautiful. So that is the third step. First step, added the acetyl-CoA group, transfer to the ACP end. Second step, transferred it from the ACP to the cysteine. Third step, added the malonyl group onto the ACP end. All right, so we've covered the third step. Let's talk about the fourth step. So let's pick up where we left off. Okay, so what do we have here on that cysteine end? Okay, that cysteine group, technically bound to the sulfur of that thiol group, is our acetyl group, right? Then on the ACP end, we should have that malonyl group, that 3-carbon structure. Okay, here's the next goal. With the first round of fatty acid synthesis, the goal is to make 4 carbons, like a 4-carbon acyl kind of chain as like the precursor, and then for the remaining steps, it'll be 2 carbons at a time. But the first one, we need 4 carbons. So how many do I have so far? I have 3 with malonyl and then 2 from the acetyl-CoA group. Okay, so that's a total of 5. That's too many. So when I combine these together, I'll get 5, so I'm gonna have to pluck one off. When I pluck one of those acetyl groups off, what is that called when you pluck off one of these in the form of CO2? It's called decarboxylation. So what we're gonna actually do here is what's called decarboxylation. And that's basically popping off a carbon in the form of CO2. Now, there's a very special enzyme that'll take these 2 carbons from the cysteine group, add it onto the ACP end, condense them, and then before it condenses, it pops off a carbon in the form of CO2. What is the name of this enzyme? This enzyme is called acyl malonyl ACP condensing enzyme. It's like, holy crap, that's one heck of a name, but this is the enzyme that's going to drive this step. So what will happen is that you will do what? You're going to kind of transfer these over here. So at the end of this, you're going to transfer 2 over, but pluck one of them off and then smash them together on the ACP end. So at the end of it, what will it look like? Well, the cysteine residue isn't going to have any more carbons bound to it. So it'll have that thiol group there. The ACP end, however, is now going to have what? It's going to have 3 carbons. We're going to represent these in red because that was the malonyl. And then it's only going to have one of the carbons from the acetyl group that was on the cysteine end because the other one got plucked off. That's a total of 4 carbons now that we've built up at this point. Okay? That is going to be the beginning of our fatty acid chain. So now that we've done that, we've gone through the first 4 steps. Let's go through a couple more where we take now this 4-carbon structure, which is in a very specific form, and we'll talk about it. It's what's in the form of a beta ketone. Okay, so we'll talk about that in just a second. But what we're going to need to do from this point on is modify the activity of that beta ketone for the remaining next steps. So let's go there. All right, so let's continue, guys. So we left off where? What do we have kind of sitting on that cysteine residue? Nothing at this point, right? We transferred everything from that onto the ACP end. So on that cysteine residue should just be that thiol group. That's where we left off. And then on the ACP end, we should have the condensed version of the 3 carbons of the malonyl, and then that 1 carbon of the acetyl group because we plucked one of them off via the decarboxylation, right? And then one of the important things that we said here is if we actually look at this entire structure and really zoom in on it at the actual like organic kind of chemistry level, we'll see here that we have that ACP group, which is bound carbon double bond oxygen there. And then again, you'll have another carbon here, you'll have another carbon there, and then you'll have this kind of structure. And then we called this the beta ketone, right? What part of this was the beta ketone? It was actually this part that was the beta ketone. Our goal for this next step here is to take this beta ketone and actually spread some electrons in the form of hydride ions across it. The ultimate goal is to turn this into a hydroxyl group. So remember I told you that there was a couple players that were involved. We said acetyl-CoA kind of gets mixed in, and then we said that malonyl-CoA gets mixed in, and then the FAS, the fatty acid synthase, is involved. What was the other one? NADPHs. They're coming in, baby. So NADPHs are really cool here. They come in, they drop some of the electrons off in the form of hydride ions. And the ultimate goal here is you're going to get the same product throughout a lot of these steps here. You're going to have this thiol group here, and then on that ACP end here, you're going to have the 3 carbons. The number of carbons isn't going to change, it's just the different structure within that 4-carbon component here that's going to change a little bit. So if we were to really zoom in, what happens now after we do this reaction? We're going to take that ACP group, we're going to have that carbonyl group there, carbon, and now where the beta ketone was, I have a hydroxyl group. What is this called? This is called a hydroxyl group. That was the goal of this 5th step here. Now there's a special enzyme that's involved in this step, which is taking the beta ketone of this acyl group and converting into a hydroxyl group. The enzyme is called, it actually kind of works out nicely, it's called beta ketoacyl ACP reductase. It's actually perfect how this is named. You want to know why? The beta ketone of the acyl group on the ACP end is getting reduced by who? NADPH. That's kind of a nice, beautiful thing there. So that's the 5th step. The 6th step, let's continue on here. Again, throughout all of these, you're going to have that thiol group. So here, we'll just, for right now, this is not going to change throughout these steps for a while. So here, let's just get these out of the way. These aren't going to change for a bit. On the ACP end, again, the number of carbons isn't going to change for a while as well. So we're still going to have 3 carbons here. We're still going to have 3 carbons here from the malonyl. And we're still going to have that 1 carbon from the acetyl group in these next steps. The only thing that's really going to change is the different components of that 4-carbon group. So what do we leave off here? We have that ACP group, carbonyl, carbon, and now we have a hydroxyl group here. What do I want to do now? The next goal is to take this hydroxyl group, get rid of it, and yank out something in the form of water. So I actually want to dehydrate this molecule. So I'm going to yank water out of it. When you yank water out of this molecule, what is it going to look like at the end? Imagine me pulling water out of this. What happens is you get something like this. The ACP You get that carbonyl group, and then again, you're gonna get kind of a double bond here. You'll get hydrogens that'll span across this, and then a CH3. Okay, so it's still 4 carbons, but now there's no longer a hydroxyl group, there's a double bond, okay? The enzyme that performs this step is very cool, okay? Now here, before we actually tell you the name of it, you know when we number things according to organic chemistry, we start with the highest functional group, highest priority, so IUPAC style, this would be the number 1, 2, 3, 4. The third carbon is the one with the hydroxyl group. So we actually use an enzyme called 3-hydroxy acyl dehydratase. Think about this. On the third carbon of this acyl group, there's a hydroxyl group. We're going to dehydrate it by pulling water out. It's a perfect kind of thing there. Okay, going to the next step. At this next point here, we're still gonna have the same component here. We still have, it hasn't changed. We still have the 4 carbons. 3 of them are from the malonyl group. 1 of them is from the acetyl group, okay? That hasn't changed. It's also gonna be the same over here. There's still gonna be a total number of what? You're gonna have 4 carbons here. 3 of them are from the malonyl group. 1 of them is from the acetyl group. Okay, beautiful. So what's changing? It's just the different components. Let's leave off here. What do we have here? We have that ACP group. We have the carbon double bonded to oxygen. We have a carbon, we have a double bond carbon, and then we have that methyl group. And then we have H's right there, okay? So this is a double bond, okay? We called this over here, we called it a hydroxyl group. This thing here, this kind of like structure here, is actually called a enoyl. What is it called? It's called an enoyl. What I want to do is I want to take this double bond that's in the form of what's called an enoyl, and I want to spread hydrogens across this entire thing. I want to get rid of the double bond. So in order for me to do that, I have to add more hydrogens across that double bond. Who did we use before to add hydrogens to things? The NADPH. It's back, baby. So NADPH comes back and adds on some hydrides. Okay, so we're gonna reduce this actual molecule here. So what is it gonna look like afterwards? Well, imagine we added hydrogens across that double bond. So carbon, double bond, oxygen, carbon, and now there's no double bond there. So it should just be a carbon here, right? We added hydrogens across this. So this should be a CH2 and a CH2 there, because I added a hydrogen to this one and I added a hydrogen to this one. So now there's no double bond. It's just a nice like saturated fatty acid. There's no double bonds present. This is our nice acyl group, okay, for our fatty acid chain. That is what we want at the end of this kind of process. Now, this thing is called an enoyl. We're reducing this. So guess what the name of the enzyme that catalyzes this? It's called a enoyl. The enoyl on the ACP end is getting reduced, reductase. And then this is the end structure here, okay? Okay, now that we have that, let's pick up here at this last part here. This is kind of our 4 carbon structure here that we've really formed out. We're pretty much at the end, guys, of this process. But let's say for a second, okay, we've really got our fatty acid kind of chain beginning. We have 4 carbons that we're gonna start with. Let's say that we continue. We're gonna continue to do this process until we can kind of have an idea here of what it's gonna look like. How do we keep adding things on? So let's say that we start back from a previous couple steps here. Remember there was another enzyme that transferred the ACP molecule, transferred the molecules from the ACP group onto the cysteine group. Do you remember what that enzyme was called? It was called acyl transacylase. And all it did is it's just going to transfer this group of 4 carbons onto that cysteine group. So what should this look like afterwards? This should look like this now. I'm going to have the 3 carbons here from the malonyl group, and then I'm going to have that carbon from the acetyl group there. Okay? All of it's going to be in this format though. That opens up the ACP end, right? So now the ACP end is open because it has that sulfhydryl group here that you can add something on. What can I add on here? I could add on another malonyl-CoA and then start this process all over again. So it's kind of just get a quick idea and to test your knowledge to see if you guys remember all those steps really, really quickly. So let's go to the next thing and see if we can review quick. All right, so let's test you guys' knowledge. All right, let's see if you guys remember these things, engineers. So we had the acyl transacylase, right? And it basically transferred things from the ACP end onto the cysteine end. Kind of that fatty acid chain that we've already kind of been forming here at this point. 3 of them were from the malonyl group, right? And then that one was from the acetyl group. And so far, it's all in that saturated fatty acid form. On the ACP end, though, it's free. It now has that sulfhydryl group that is ready to bind onto something. So now what we're going to do is we're going to use that enzyme. What was the enzyme before? That we utilized to add in a malonyl-CoA, and in the process we spit the CoA off. That was called malonyl transacylase, right? So that was called malonyl transacylase enzyme. So that enzyme is going to stimulate that step to add the malonyl group onto the ACP end. So what should this look like at the end of this now? So you're still going to have that 3-carbon thing there from the malonyl group, but now you're going to have the 3 carbons here from this new malonyl group on the ACP end. And then we still have that 1 carbon from the acetyl group there, okay? This is what it should look like. And then what was the next step? After that, we want to do what? We said the first thing you should have 4 carbons as the beginning building block for fatty acid synthesis. From that point on, how many do we want to add? We want to add in 2 carbons kind of at a time. So now what I'm going to do here is I'm actually going to add this whole kind of group here on. And in the process, I'm going to have to pluck one of those carbons out. So I'm going to condense it down and pluck a carbon out. So that's what we're going to do here in this kind of following step here. All right, so if we continue here, right? So let's say here again, we have the 3 carbons from the new malonyl group. We have the 3 carbons from the old malonyl group from the first cycle, and then that 1 carbon of the acetyl group, right? What's the goal here? The goal is to go back to what we had when we had that condensing enzyme. You know the condensing enzyme that we had before? It's basically going to combine this carbons here onto this one. And then what did it do? It plucked out one of the carbons in the form of a decarboxylation reaction, right? So it popped off one of those carbons here. Let's just say that we pick any of them. We're just going to say that we pop that blue one off there since it's just so random. Okay, so we're going to pop that off in the form of a CO2. That's called a decarboxylation reaction. Okay? Now, what would that look like after I fuse these 3 red carbons with these 3 red carbons here? It would look like 6 red carbons, right? So I'm going to have 1, 2, 3, 4, 5, 6 here. And then I transferred them all from the cysteine group. So is there anything on the cysteine group? No. So it's going to have that thiol group there on the end. Remember what I told you. The first round of fatty acid synthesis, there's going to be 4 carbons as the building blocks. From that point on, from every remaining cycle until you build a 16-carbon fatty acid, you add 2 at a time on. Okay, so these were the OGs. These were the original 4. And then these are the additional 2 carbons that we're going to keep adding on one after another, after another, after another. So here's what I want you guys to remember, because this may come up on the exam. If there was a 16-carbon fatty acid that you had to make, the first round was 4 carbons. So that's a total of 12 carbons. Okay? How many rounds would you have to go after that first cycle? How many times would you have to do what we're doing now until you make a total of 16 carbon fatty acid? Well, 2 carbons at a time, so 12 divided by 2 is going to be 6 rounds. So I have to do 6 additional rounds from the first time that I started. So it's a total of 7 rounds for fatty acid synthesis to occur. All right. What was the name of this enzyme? Just to test your knowledge. When we condensed it down, we condensed the malonyl group with the acyl group. It's called the acyl malonyl ACP condensing enzyme. All right, beautiful, and that was catalyzing this step. Now, from that point on, what do you guys remember? Well, here, we're gonna have our 6 carbons here, right? And then we're going to keep building on. So 1, 2, 3, 4, 5, 6. If you guys remember, let's see if you guys remember here. This is going to be in the form of a beta ketone. We go from the beta ketone, right? We take the beta ketoacyl ACP reductase, and eventually we're going to convert this into a hydroxyl group. Then we're going to take another enzyme called the 3-hydroxyl ACP dehydratase and pull water out of this, and that is going to give you a double bond here, right? That's going to give you your enol group. And then the last step is that we were going to do what after that? Then after that, we're going to take and splash hydrides across that double bond, and then eventually convert this into a kind of a growing fatty acid chain in that sense. We're going to saturate that. So at the end of this, it's still going to be, after we went over all these remaining steps that we've already talked about before, it's still going to look like this. But let's imagine that we continued this step over and over and over and over and over again. What's going to be like at the end of this? You're just going to continue to keep building on 1, 2, 3, 4, 5, 6. This is going to look the same after you do all of these steps that we talked about before, right? Going from the beta ketone to the 3-hydroxyacyl group to the enol and to the saturated fatty acid. And then what will you do there? You'll transfer that onto the cysteine group, and then you'll start the whole process all over again, right? But let's say that we just continue to keep doing that. So let's come down here for a second. Let's say that we continue, we do a whole 6 rounds from that point on. And eventually, we have at the end of this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have my 16 carbon fatty acid, which is bound to this ACP group. I want to liberate this fatty acid away from this fatty acid synthase. How do I do that? There's a special enzyme called a thioesterase, which is going to be utilized to cleave this completely grown 16 carbon fatty acid. So this is a 16 carbon fatty acid in the form of what's called palmitate or palmitic acid, one of the two. We cleave that from the ACP end, and that is how I grow my fatty acid chain. Okay? Ninja Nerds, I hope that made sense. All right, Ninja Nerds, in this video today we talk about fatty acid synthesis, and this is part 2. I hope it made sense. I hope that you guys did enjoy it. As always, Ninja Nerds, until next time.